Okay, everybody, we're going to get into hypothesis testing, Chapter 9. This was one of the biggest pieces of the entire class, was to make sure we can do a hypothesis test. I know on the syllabus it lists sections 9.1 through 9.5, and that's because that's what our textbook does. It takes these ideas and it breaks them into 5 sections. What the notes do and what the homework does is it really just separates them into 3 sections. There's a section on doing hypothesis tests on proportions. That's what we'll do in this video. Then in the next video we'll do hypothesis testing on means. And then the third part of Chapter 9 will be addressing common errors that can occur when doing hypothesis testing. So I know it says 9.1 through 9.5 on the schedule. Those are the sections in the book, but the notes and the homework have condensed it down into just 3 sections, so there's only 3 homework sections from Chapter 9. Anyways, let's get right into it. So, one way you can do a hypothesis test is actually by using confidence intervals. Okay, and because of that, you're going to notice that the process and the procedure for doing a hypothesis test is incredibly similar to the 5-step process we use when doing a confidence interval. Really, really, really closely related. So anyways, here's our goal for this section. We want to be able to understand the logic behind a hypothesis test, interpret the p-value of a hypothesis test, make sure we know what it means to be statistically significant, and ultimately know how to do a one-proportion z-test. Now, if you remember with confidence intervals, the procedures we learned, there was a 1-sample z interval and a 1-sample t interval, and we used both of those when we were talking about means. Well, we're going to learn the same thing, but we call them a test as opposed to an interval. And then we also learned in 8.3, I believe, about a confidence interval for proportions, and we learned about the 1-proportion z interval. Well, this is going to be the 1-proportion z test, okay? Really, really closely related. So here's the general idea of a hypothesis test, and the first 3 pages of notes or so, maybe 4 pages of notes, slowly break down the idea. But kind of like with confidence intervals, I think you actually have to get your hands on them and do an example all the way through. And by the time you've done a few of them, these things get very rhythmic, they get very routine, and it's just, rinse and repeat type of a process. So the last page is what actually has our full-blown do a hypothesis test example. Everything else is just working up to that. So the idea behind a hypothesis test is we want to test whether or not a claim about a parameter is true. So remember, the parameters we're typically interested in would be the population mean or the population proportion, and in this section we're only talking about the proportions. Okay, so here are some examples of things we may want to test. Will at least 52% of voters approve Measure B on an upcoming election? By doing some data collection, we can determine statistically whether or not that's likely to happen. Jerry claims that his car averages 37 miles per gallon. By doing some data collection, we can statistically show that that statement is true or not true. Okay. All right. So actually, I take that back. We don't ever show something as true. We just show that it's false or not false, and that's going to be described a little bit down here below. You could read over the different types of claims that we can test, but basically any sort of question, we now are going to be able to mathematically determine whether or not something is essentially true or false. Okay, so here's one issue. We don't know, and generally we can never know the true value of a parameter. So for some population, most things, it's hard to know the population mean or the population parameter. And that's just because it's always changing. You would have to do a census, so it's very hard to actually pin down that number. So what that means is that we can never actually prove that something is true. We can only hold on one second. Okay, I'm back. We can never actually prove that a claim is true. That's not what our goal is. Our goal is to basically either prove that the claim is false or we can't say that it's false. Okay, so that's the idea of what we can do. We can use a statistic, right, which is an estimator. So the statistic is usually the sample mean or the sample proportion, and we could use that as evidence as to whether or not the given claim is true. And again, it's not like we're not necessarily saying the thing is true as much as we are saying that I can't. There's no reason for me to assume that it's not true. Okay, either there's going to be some sort of claim, and we're actually going to learn to call that the null hypothesis. And we're either going to be able to say that, yep, there's no reason to doubt that, or there is reason to doubt that. Okay, that's essentially what's going to go on with a hypothesis test. Okay, so they use this analogy of a trial, and this is a decent analogy for kind of how we approach the idea of a hypothesis test. You know, it says in the U.S., if a man is on trial, then in our judicial system, we must do a few things. First of all, the person's innocent, right? We assume that they're innocent. And then we collect data, gather evidence and collect data. And then we show then that if the person really was innocent, then the evidence would be really unlikely to happen, or the evidence would be extremely unlikely. So in other words, it's more likely that the person is actually guilty. Does that make sense? So again, we always assume that someone is innocent, and then we collect a whole bunch of evidence about that person or the scenario. And the idea is to say, well, if this person really is innocent, then all this evidence, it's unlikely that we would be able to gather all this evidence claiming to the contrary. It would be so unlikely that it's statistically, we don't have much faith that it's going to be statistically going to happen. It's going to be a very low probability of getting that evidence if the person was indeed innocent. And so therefore we would kind of lean towards, well, we think they're guilty. Okay. Same is true for a hypothesis test. We're going to be testing something about a parameter, about the population mean or population proportion, and we assume that a particular value is true. And then we collect evidence, do some sampling and collect some evidence. And then what we basically do after that is we're going to show that the assumed parameter value, show that given the assumed parameter value, the data and statistics would be extremely unlikely to occur, and so therefore it's more likely to believe that we were wrong about our original assumption. We were wrong to assume that the person was innocent based on all this, based on the unlikelihood of finding all this evidence. And so that's the same idea here. We were wrong about our assumption of the parameter based on the evidence we have found that kind of goes in the face of that assumption. So more formally, here are the steps. Well, part of the steps. We start by defining what we call the null hypothesis and the alternative to that hypothesis. Okay. We then look at data and calculate a statistic, or calculate the statistic. All right. We then find the probability of getting that statistic, the likelihood of getting that evidence, and that's known as the p-value, the likelihood of getting that evidence. Now, if the probability is small, then we reject our original assumption. Okay, so in other words, if we have some assumption and we find evidence based on that assumption, and the probability tells us that it's incredibly unlikely that if that assumption were true that we should be finding this evidence, meaning we shouldn't be finding this evidence, then what we do is we basically say, well, I think we were wrong about our original assumption. Maybe the person's actually guilty and not assumed to be innocent. Okay. So we're going to do two things. Again, we're going to have some assumption that we assume to be true, and we are either going to reject it or we're not going to reject it, right? We're going to leave the assumption as, yeah, well, we assume he's innocent and we can't prove to the contrary, so you stay innocent. Or the evidence is going to say it's very unlikely that you're innocent if based on this evidence, so we will reject that claim of innocence. Okay, I hope that idea kind of makes sense. I know it will once we actually get our hands on a problem, okay? So they're kind of easing us into this idea. So here it says that Jessie takes a 20-question true or false quiz. She claims that she guessed on the entire quiz. Would you believe her claim or reject her claim if she got 11 out of 20 correct? Okay, so here's her claim. Well, we know she took a 20-question true or false quiz, so there's only two answers, true or false. Her claim is that she guessed on the entire quiz. So at the end of the day, if she scored 11 out of 20, would you believe that she did indeed guess? I would. I mean, because if it's only true or false, don't we kind of expect 50-50 to be our results? All right, so if she got 11 out of 20, that's almost 50-50, so yeah, I would believe her. Okay. The probability of guessing 11 out of 20 is not low. It's not unlikely. Right? If it was unlikely, then we would see a very low probability of this occurring, in which case I would not believe her. Now, what if she said, oh, I guessed everything and I got 19 out of 20? That's kind of suspicious because it would be very hard to get 19 out of 20 just based on guessing. That has a very low probability, a low chance of happening. So if she got 19 out of 20 and she claims she guessed, we would probably think, I don't think you guessed. I think you might have, whatever. You just didn't flat out guess each time. You either knew the answer or you looked up the answer or something. So here I would not believe her claim. That she guessed. The probability of guessing 19 out of 20 is very low, very unlikely. And it's so unlikely that we're going to assume that, the statistics are going to say that it's so unlikely to happen that it makes us want to not believe her. We're going to think that she didn't just guess. Now, by the way, up in the beginning it mentioned a p-value. Oh, right there's a p-value. This is your p-value. The probability of doing that thing, okay? That's the probability of achieving that amount of evidence is the p-value. And if that p-value, the probability is low, and we're going to determine what we consider too low, we would then reject her claim. Okay. All right, so let's take a look at the next page where they cover the 5 steps for a hypothesis test. Now, just like we did with confidence intervals, we always need to follow these 5 steps. It makes sure we're doing a proper, complete procedure. It doesn't let anyone argue with our results at the end of the day. And it also really helps us to walk through the problem because it's just writing basically a list of steps to follow, to walk our way through a hypothesis test. So the first step is always define the parameter and hypotheses. So define the null and alternative hypotheses and state the level of significance. And we'll get to that in a sec. What that level of significance is that is the cutoff for what we are going to consider too unlikely or too low of probability. Okay, so we'll get into that. So that's similar to what we did in the confidence interval. Step 2 is exactly the same as what we did in a confidence interval. You would then name the test, right? And at this point, all we are going to have is a test for proportions. We'll use a z-score for our critical numbers, so it's going to be a 1 proportion z-test. We're going to check the requirements just like we did in a confidence interval, independent, random, and large. Just like in a confidence interval, step 4 is where you actually do the thing, where you actually take the calculations. It's just here we're not doing a confidence interval. We're finding the test statistic and the p-value, which we'll get into. And then also, just like confidence interval, the last step is to sum everything up, state your conclusion. So again, these will feel ridiculously similar to confidence intervals once you get your hands on them and get familiar with both ideas. Okay, so the first step, defining the null and alternative hypotheses. Okay, so the null hypotheses, which again we state as H naught, okay, and we say that subscript of 0 as H naught. First of all, it's always going to be a claim about, so it's the claim that we will assume to be true, and it's always going to be a claim about the population parameter. So the population mean or proportion, in this case proportion for this section. Here's the big thing. It always involves an equal sign. Always your null hypotheses will be the parameter equals something, whatever that assumed value is. Okay. The alternative hypothesis, which we write H sub A, right? The alternative hypotheses, that will be also about the population parameter, but it could use not equals, it could use greater than, or less than. It could use any of those. It's basically not an equal sign, but any one of these inequality signs. And whatever goes here, whatever your claim is, it's going to be the same here. So if you think, for example, we say that, okay, in this population, maybe P represents the percentage of folks that claim to be Democrat. And so we're going to say we think that's 70. And maybe your alternative is, I think it's actually less than 70. So I would say P is less than 70, 0.70. What I'm getting at is these numbers here are always the same. So a null hypothesis always has an equal sign. An alternative will use one of these, but they will always use the same parameter and the same number. Okay? Okay, so this is just talking about one-sided alternatives or two-sided alternatives. Basically, when it comes time to find the p-value, you're going to end up finding a z-score. We're going to see that I'm going to look for a z-score, and I'm either going to be looking for the area above the thing, that's if I went with a greater than sign, or the area below that z-score, that's if I went with a less than sign, or if I went with a not equal to sign, I'm looking for the area outside the tails there. Okay. The area under this curve is probability, and that is the p-value. Okay. And depending on the size of the p-value and what we're okay with, we're either going to reject that original claim or we won't reject the original claim. Okay. Again, this is really hard when we're not together, so I can't see the look on your face and know if it's confusion or frustration or what, but just hang in there. Get some examples under your belt. Guarantee these are going to be okay. All right, promise you. Some other tips for writing hypotheses, we always use parameter notation. So mu or p for the population proportion, or if we're talking about standard deviation, then the population standard deviation sigma. We do not use statistic notation, remember, which is what comes from our sample, like the sample mean and sample proportion. Okay, and when we are using some formulas, here they say think about the alternative. Generally, I think when you read the problem, there's going to be a natural way to make this selection. That's what they're talking about here, is give some thought. Don't just pick randomly not equal or greater than or less than. Look at in the problem, and there's going to be one of these that makes sense. And again, you'll see when you get your hands on some examples. There's going to be one formula we need to use, and whenever we use the population values from our null hypothesis, like again 0.70, if I'm going to use this in a formula, or I'm going to refer to the population mean in a formula or proportion, we use the subscript p naught just to kind of indicate that that's the value that's coming out of my null hypothesis. They kind of copy that subscript. So you'll see that in formulas, and again, it's just meaning that it's referring to this value here. Okay. The first example or two just has us write down a null and alternative hypotheses. So these notes are gonna have us slowly do a hypothesis test, one step at a time, and then they're gonna cut us loose and say, okay, now do this problem. So right now we're just talking about writing the hypotheses. It says, in order to win an election, you need to get more than 50% of the vote. A sample of voters was polled to see if you are likely to win. Write a null and alternative hypothesis to see if the poll supports a win in the actual election. Okay, well, the null hypothesis has to do with either the population mean or proportion, but here we're talking about percentages. We're talking about a proportion. It always uses an equal sign, and so it wants to know what the kind of the bar is, the status quo would be. And in this case, it would be that we get 50% of the votes. Okay, only 50%, or actually it could be less, because we'll see that it's the complement, basically, of what we write for our alternative. The alternative, the thing we are trying to test, or that we're kind of hoping is true, is we hope we get a win. Okay. Well, if we get a win, that's what we're wanting to test, is to see how likely we get a win. To get a win, I've got to get more than 50%. So of your choices, greater than, less than, or not equal to, which one goes with more than 50%? It's greater than. So my alternative would be, nope, the proportion is greater than 50%. Okay. So we are going to then gather evidence and find a p-value and blah, 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 blah. But basically, at the end of the day, we're going to say the evidence suggests that we can reject this and go with this, and we win. Or there's not enough evidence to reject this, and so therefore we just stick with the status quo, and we would not go with the alternative. All right? Okay. Let's try next example. Same deal. They're just having us write the the hypotheses. So it says John claims that his free throw shooting percentage is 85%. To prove it, he shoots 50 shots and makes 37 of them, giving him a 75% shooting percentage. Write the hypothesis used to test his claim. All right. So John claims that he shoots 85%, that he makes 85% of his free throws. And he says, I'll prove it. And he takes 50 shots, but he only makes 37 of them. Now, 37 out of 50, I'm assuming, is 70 or 0.75. That's how they're getting, that 75% shooting rate. So, the null and alternative hypotheses. Well, the null hypotheses, again, what's the parameter that's being studied? Is it a mean or a proportion? It's a proportion because it's a percentage, and proportions are percentages. The null hypothesis always uses an equal sign. What is the status quo? What is the claim? John claims that he's at 85% or 0.85. That is the baseline claim, and we assume that's true unless the evidence suggests otherwise, right? We assume innocent until proven guilty. We assume that's true unless the data suggests otherwise. The alternative to that, well, again, it's always the same variable. It's always the same number. It's just, should I use greater than, less than, or not equal to? What do we think the alternative to this claim would be? He claims 85% is his shooting percentage. Based on the data we see, in our one sample, he only shot 75%. So don't we think that his proportion or his shooting percentage is actually less than 85%? So that's what I meant, that when you read the problem, there's sort of a logical one that jumps out at you based on either the way the question is asked or what the data suggests. Okay, and so again, continuing on, this would just be step one of the test, all right, in addition to listing the significance level, which we'll talk about shortly, and then we would move on to step 2, 3, 4, and eventually we would make our case. Okay. Step 2, you notice they skipped it here. We went from step 1 to step 3. Remember, step 2 I'll just add it in here, is where you name the process. And the only thing we have at this point is a 1 proportion z-test. That's what we're going to learn how to do right now. So later when we learn about means, then you'll have a 1 sample z-test and a 1 sample t-test, similar to what we had with intervals or confidence intervals. But for now, this is the only guy we've got. All right, step 3, check IRL. Remember, we don't want anyone to be able to blast holes in our argument at the end of the day, so this makes sure we're doing good statistics. We hope that our data is independently collected. Again, generally our data may not be independent, but most of the time we can rely on that 5% rule and say, well, our sample size is less than 5% of the population size, so even if it's not independent, we can safely treat it as though it is. We really hope that our data is being randomly collected somehow. And then remember, for proportions, large enough means that the number of successes is greater than or equal to 10, and the number of fails is greater than or equal to 10. And remember, the whole reason for that was, again, based on central limit theorem. If that's the case, then we know when we find our p-hats that they're going to be nice and normally distributed, right? And that's what we want, because that's how we're going to calculate probabilities, using a normal curve. All right. Quick little recap on what a z-score does, and then we're going to see how we can bend it just a little bit to what we need. So this is what we've, learned about a z-score. Remember, your z-score is your data value minus your mean over the standard deviation. And if you remember, what the z-score does is it tells how many standard deviations my data value is from the mean. It tells us how many standard deviations my data value is from the mean. Okay. Now, we're going to take that and just, we're going to use that idea, and we're going to find what we call the z-test statistic. It's basically like we're finding the z-score, but we're doing it for our test statistic. Okay, so our z-test statistic is found by taking the statistic from my sample, so my sample mean or my sample proportion, minus the parameter. Now again, remember the parameter, they're using the parameter found in the null hypothesis, so that's why this formula uses that sub-zero, because that's how we write our null hypotheses, with a sub-zero there. And we divide that all by the standard deviation, right, of the statistic, which we would find here. Remember, this is how we find the standard deviation based on what the central limit theorem tells us, right? And this is, again, why we want our number of successes and fails to be big enough, because we want these guys to be normal, because when this happens, our data is normal, and that's how we find our standard deviation according to that theorem. Okay. All right. What the test statistic represents is it is the number of standard deviations that our result is from the expected parameter. Okay, so, we expect a certain percentage, like John expected a 85% free throw shot. We found from our sample that he only got a 75% free throw shooting percentage. So what this z-test statistic does is it takes that distance, the distance between them, and it standardizes it in terms of standard deviations. It tells you how many standard deviations away our sample was from what the claim was. Okay, so let's give it a shot here. It says, back to that same example, John claims his free throw shooting percentage is 85%. To prove it, he shoots 50 shots and makes 37, therefore giving him a 75% shooting percentage. if John was really telling the truth, how many standard deviations below the true shooting percentage did he shoot? To find my standardized test statistic, I'm going to take the sample proportion that I found minus the claimed proportion divided by the standard deviation based on that claim. That's why we're using P naught and Q naught, because it's based on the claim. All right, well, this would just be 0.75. That's the percentage or the proportion that he actually did from the experiment. The claim was that he claims he's at 0.85. Now, if I'm going to do the standard deviation based on the claim, I would take P naught, which is 0.85, times Q naught, which is the complement, 0.15, over N, the sample size. And if you crank that out, you get negative 1.98. He shot negative 1.98 standard deviations below the expected value. So he shot 1.98 standard deviations below what he claimed. And maybe you're already starting to get a sense of where we could use this. Would you consider that to be unusual? 1.98 standard deviations below the claim, below the mean or below the proportion, the population parameter. I think we would probably say that's close, but that's not unusual. What's our cutoff for unusual? Isn't it usually 2 standard deviations above or below, right? That's when we say, oh, that's a little too far out. That's extreme. So what this is sort of getting at is it's sort of saying that, yeah, this was low, but I wouldn't say it's unusually low based on that being his claim. Now, if he claimed that he shot 99% shooting or, free throw percentage, and then he goes and posts a 75%, well, then he's going to be more standard deviations away, and we'd say, yeah, that's a little too far away. We think your original claim is off, all right? But in this case, it probably isn't off. It's probably that, yeah, that was maybe just a bad run, but it's not extremely far enough away to say that we reject that original claim. He might be right about 85%. That's where we're going with this. So after you find this critical z-score, the next thing you're going to do is find the p-value, which is simply the likelihood or the probability of getting that or something more extreme. Okay, so that's what the next page is, and then we will finally be cut loose and do a full-blown hypothesis test. Okay, so the p-value. The p-value is the probability of obtaining the observed value of our statistic or one more extreme. Okay, so again, it would be back to here, it would be back to the John example, it would be the probability of John shooting 75% of the free throws given he claims 85%. It's going to be the likelihood of that happening. Now, what we just did on the previous page is to calculate this probability. We basically converted these numbers into a z-score, so I could... Sorry, guys, kid was crying. Where was I? So I'm kind of forgot now. But anyways, again, the p-value is the probability of obtaining this result based on what was claimed. Okay? Oh, I see. I was going to say, to calculate that probability, again, what we did is we found the z-score, right? There was a claim, and didn't we find a z-score of like negative 1.98? Now, the p-value is the probability of getting that score or one more extreme. In this case, being more extreme, we would consider that being even worse than 75%. So this line represents exactly the 75% mark. Our alternative is basically saying that, no, we think you're below this 85% mark. So we are looking for the area below our test statistic here. Now that you can get right off of StatCrunch or your z-table, and what that area is, that is your p-value, okay? All right. So what does it mean to be statistically significant? We say that a result is considered to be statistically significant if it is unlikely to happen by pure chance. Okay, so in other words, if we go ahead and get a p-value, a probability that is so low that it just seems like, you know what, that couldn't have just been a bad run at things. I think you were wrong about your original claim. We would then say, well, then our sample was statistically significant, okay? Again, we didn't crunch the numbers or find that area, but I have a feeling that this was maybe just a bad run and that he's probably not wrong about his claim that he shoots 85%. Again, we would need to find that area, and there's a little something we would have to do first, but it's not more than 2 standard deviations away, which is what we typically consider to be unusual. So if it is far enough away to be considered unusual, then we would say that our result was statistically significant, all right? That it was not caused by pure chance or a bad run at things, that the claim was wrong. Okay, now I said that we need to do a little something first, and that's what this is, and this should be done in step 1, okay? Before we do our experiment or our hypothesis test, and it's really important that you do it beforehand, we must determine what do we consider to be too unlikely to happen. Right. So back here, I was using the idea of 2 standard deviations away is considered to be unlikely. Now, if you remember, using empirical rule, 2 standard deviations left and right is 95% of my data. So anything outside of that would be 5% of my data. So if I found a p-value that was lower than 5%, you know, the probability of him shooting the probability of him getting this shooting rate, given that he claims that, if there's only a 5% chance of getting that number, that's very low, okay? And so what that means is that I don't think it was just bad luck, because it's really unlikely to happen. I think you're wrong about this claim. That is our significance level. How small of a probability do we want to consider too small? And you get to choose that. So a very common one is 5%. We often compare our p-value to 5%. Okay? That is our level of significance. However, you can choose any level of significance you want. So some very common ones are 1%, 5%, and 10%. Again, if you were choosing yourself, I would make 5% my default. Okay? However, it is incredibly important that you do this beforehand. That's why you do it in step 1, before you get your results. Because sometimes you'll get a p-value that is really close to 5%. Like maybe your p-value comes out to be 6%. Well, depending on what you chose as your level of significance, your threshold for what you consider to be too low or too high of a probability, or too low of a probability, in one case you might reject the claim, and in another case you might fail to reject the claim. Okay, and so you can't look at your results and then decide, well, do I want to reject it or not reject it? That defeats the purpose of the hypothesis test. Decide ahead of time how low is too low for the unlikelihood, okay, what you're comfortable with, and then based on that, you will either reject or fail to reject the null hypothesis. Okay, so when writing up your conclusion, this is the last step, step 5, right? By the way, this up here was step 4, was find the z-score and then the p-value. That's step 4. If your p-value is lower than what you're okay with, alpha, again, is your level of significance, okay? And if your p-value ends up being lower, meaning the probability of the the probability that the data would come out the way it did based on the claim is lower than what you're comfortable with, then what we do is we reject the original claim. Okay? So since a p-value of whatever percent is less than alpha, we reject the null hypotheses. And we would say there's sufficient evidence to show that blah, 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 that the alternative is true. If your p-value is higher than your level of significance, in other words, if we say, well, the bare minimum we're okay with is 5% probability of this happening, and it turns out that the likelihood of the data occurring the way it did based on the claim was 10%, we'd say, well, that's low, but it's not lower than what we were okay with, so there's no reason to get rid of the claim. We do not reject the claim. We fail to reject the claim. Kind of like what I was doing here with the basketball thing. Again, I haven't found the p-value, the actual probability, and I didn't set a threshold to begin with, so I'm not going to, but I'm just saying that since I'm not more than 2 standard deviations away, I think that though this is low, it's not low enough for me to want to reject the original claim. I would fail to reject the original claim because there's not enough evidence to suggest that the alternative is true. All right, so since the p-value of whatever it is greater than alpha, we fail to reject the null hypothesis, and there is not enough evidence to show that the alternative is correct. Okay. Let us do, I think, is this asking us to do a full-blown hypothesis test or just pieces of it? Let's see. It says the percentage of all college graduates in the nation who have LinkedIn accounts is 32%. 275 graduates from one particular college had 38% of its graduates with a LinkedIn account. How many standard deviations above the overall percentage is the particular college, and what is the probability? Okay, so they're actually just having us find the test statistic and the p-value. They're not having us do a full-blown test yet, so we're really just kind of doing step 4 here. I think it's sort of easier just to do the whole problem, but let's see. First of all, let's think about the null and alternative. The null hypotheses. What's the baseline claim? Okay, what is the thing that we're going to assume is true unless the data suggests otherwise? The assumed claim should be that the percentage of all college graduates in the nation that have a LinkedIn account is 32%. So the percentage or proportion of college grads with LinkedIn is 32%. That's the claim. And maybe that's right. Maybe not. We're going to see that based on what our sample says. What do you think our alternative should be? Look at what our sample showed. Our sample showed that out of 275 grads, 38% had LinkedIn. So when it comes to picking the alternative, again, it's the same parameter, it's the same number. You just need to decide, do we think the alternative is more or less or just flat out not equal? If you can, it's better to choose more or less. Okay, it's better to choose more or less for most problems, but sometimes they ask you to do not equals. Since our sample had a higher percentage than 32%, I think it makes sense that our alternative would be, wait, this should be 32, sorry, not 0. Our alternative should be that there is a larger percentage of students that have LinkedIn. Okay, so I'm just kind of putting that off to the side because we'll need that when we calculate the p-value. So let's find the test statistic first. Now, if you remember, the test statistic, z, is equal to the statistic we found minus the claim divided by the standard deviation based on the claim. And again, for proportions, this is how you find standard deviation. For means, there will be a different formula. Okay. So let's see. We observed a statistic of 0.38. 38% of our college grads were on LinkedIn. The claim is that 32%, so 0.32, are on LinkedIn. The standard deviation, oh man, I'm out of room here. Let me just do it off to the side. So the what we found was 38%, the claim was 32%, and the standard deviation based on the claim, well, the proportion that they think has LinkedIn would be 32%. So Q naught would be the proportion that they think does not have LinkedIn. The complement would be 0.68. And that would be all divided by n, the sample size. And if I do that, and if I did everything right, I got 2.13 out of there. Okay. Do be practicing these on your calculator because they're hard to put in and they're easy to get wrong. And you need to do things like you need to keep the numerator in its own set of parentheses to keep the numerator separate from the denominator. You probably need a big set of parentheses once you open the radical. Make sure you're trying it and can get 2.13. Anyways, that is my test statistic. So, if I'm thinking of my normally distributed p-hats, the p-hat we observed is way up here. It's at 2.13 standard deviations. Now, what we need to decide, the p-value is the area under the curve either left of that score or right of that score. Well, we were interested in our alternative being greater than that. So anything that is more extreme, because again, remember the p-value is the likelihood of getting that value, or anything more extreme. More extreme in the case of our alternative hypothesis would be something even bigger than 38%. So more extreme would be something even more, a higher percentage of students have LinkedIn. So that right there, that area is my p-value. That's the probability of getting that observation, right? That's the probability of getting that observed value based on the claim that only 32% of students should have LinkedIn. Okay, so my p-value is the probability that I get a z-score greater than 2.13. Now, I can do this on StatCrunch, or the whole reason we converted to a z-score is so that I could use a z-table. So I'll go ahead and do it with the z-table. Stats tables, it's a positive z-score, so let me go to my positive z-table. Now this is a little annoying because remember my z-table only tells me left area. I said I want the area to the right of 2.13. That's what I want. So let me find 2.13 on the table. 2.13, right? So they're going to meet right there. So that tells me that this area here, that area is 0.9834. All right. Well, I want this area. So to get that, aren't I going to need to take 1 minus the green area I do not want? 1 minus 0.9834 would be 0.0166. That's my p-value. That's the area under the curve here. The probability of getting that observation or something more extreme. Oops. Let's see. Okay, here. So here I got a p-value of 0.0166. This is very low probability. That's less than, or that's just over 1%. Very unlikely. So again, the thought of being able to get a school that has 38% of its graduates on LinkedIn, based on the claim that only 32% should be, it's very unlikely that we'll get a school to show 38% of their folks are on LinkedIn. That makes us want to believe that I bet that original claim is probably off. It's probably wrong, because we know that this school has 38% of their students on LinkedIn, or at least from our sample. Okay, and so either that happened just by dumb luck, right, just randomness, or the original claim was wrong. Well, since it's so unlikely to happen, we could say that, well, we think dumb luck is ruled out. We don't think it's just by chance. We think the original claim was off And that's why we got such a low likelihood of getting this result, even though that's the result we got. Okay. Now, I can't make my conclusion because I didn't first determine what was the level of significance I'm comfortable with. What was the threshold? If I said anything below 5% and I'm going to reject that original hypothesis, then I would reject. But if I said anything below 1% is my threshold and I'm only going to reject the null hypothesis if my probability is under 1%, then in this case I would not reject. I would fail to reject. So again, that's why you have to determine this from the very get-go before you see your p-value. Because once you see the p-value, then you could make the test kind of come out however you want. You can pick an alpha that's either going to fail or fail to reject or reject the null based on your p-value. Okay. The last one is one full-blown example. So again, I hope you're feeling okay with this. You might need to watch this, or what I would recommend you do is watch this example more than once. But just like confidence intervals, every hypothesis test, what we're going to do right now is going to be exactly how you're going to do every single hypothesis test, for a proportion at least. For a mean, you're only going to change very slight little things. It's only the standard deviation. How we find that is different. But these 5 steps will be identical. Okay, so I hope it made sense up to here. I know in the beginning it sort of doesn't. You almost need to hear this a few times or do a few of these. But I recommend you go through this example more than once. And in class, we will do a bunch of these together in class. Okay, so here's the scenario. And again, they've given us the 5 steps to follow for doing our complete hypothesis test. Okay, so here it says that a large city's DMV claimed that 80% of its candidates passed the driving test, but a survey of 90 randomly selected local teens who'd taken the test found that only 61 passed. Perform a test to see if the pass rate for teens in this location is significantly lower than what the DMV claims. All right, so let's again wrap our heads around this. The DMV claims that 80% of their candidates pass. Okay, but when we took a survey of 90 people, we found that only 61 of those people had passed. There were 90 teens, only 61 of those teens had passed. So what's that percentage? That's our sample proportion. 61 out of 90, let's see what that is. Oops, 61 divided by 90 is 0.677, or let me just round it to 678. So the DMV claims 80% of folks pass. From our sample, we only found 67.8 of the people we talked to passed. So was that dumb luck? Was that a fluke? Or is the DMV wrong about their claim? That's what we want to determine. Perform a test to see if the pass rate for teens is significantly less than what the DMV states. So again, we got an answer that's less, but maybe that was just luck of the draw. Maybe the 90 teens we asked happened to be bad drivers, and so they just failed. Or maybe the DMV is wrong, and it's not the case that 80% of everyone that takes the test passes. Okay, maybe it's different for teens. So, step 1, define the parameter and define the null and alternative hypothesis and the level of significance. Okay, so the null hypothesis is the baseline claim, what we assume is true unless the data suggests otherwise or the statistics suggest otherwise. So what we would assume is true is that the DMV is right. The proportion of people that pass is 0.80, right? Until the math tells us otherwise, there's no reason to not believe it. Now the alternative to that would be that the proportion, remember, it's always the same variable, same number. It's just we decide, is it greater than, less than, or not equal to what they state. If you can, again, always go with greater than or less than. What do we think? I mean, aren't we thinking that, I think the DMV is wrong. I think that the probability is actually, or the percentage of folks that pass is actually lower than 80% based on what we're seeing here. We only got 67.8% to pass. So I would say the alternative is that the proportion is lower than 0.80. And I'm going to let alpha equal, we get to choose, so I'm going to go 5%. And again, that's sort of always the default for me is 5%. Okay, step 1 done. Step 2, name the test. This is a 1 proportion Z test. Done. Step 3 is check the requirements. Again, what they mean is check IRL. Are we independent? Are we random? And are we large enough? Okay, well, independent. Again, we don't really need to debate whether or not it's independent or not. I mean, maybe if some of these 90 teens knew each other and all their friends are bad drivers, maybe they're more inclined to be a bad driver or a good driver. I don't know. We don't need to debate it. I think we can safely say that 90 is less than 5% of all people that go through that DMV. Safe to assume 90 is less than 5% of all driving test takers. So we can treat this as independent. Okay. Do we use a random sample? Yeah, well, it says 90 randomly selected, so we don't know what the process was, but yes, a random process was used. Now, are we large enough? Remember, for a proportion, large enough means the number of successes, which is n times p, if you want to do it that way, that has to be greater than or equal to 10. They actually told me 61 people succeeded in passing, so that's greater than or equal to 10. And therefore, the number of fails, the number of people that didn't pass, is n times q. But if out of 90 people, if 61 passed, that means 29 did not pass. That's bigger than 10. We're good. And so that means, so yes, large enough for p hats to be approximately normal. And that also tells us that how to calculate the standard deviation for these things, which is what we're going to do in the next step. All right, so step 3 done. And that's always one of the more annoying steps. Step 4 is when you actually do the thing. Calculate the test statistic and the p-value. So step 4, first thing I'm going to do is I'm going to find the test statistic. Remember, I'm going to find the z-score that goes along with finding that percentage based on that claim, right? So remember, it's always the proportion you find from your sample minus the claimed proportion over the standard deviation based on the claimed proportion. So this would be what we found from our sample was that 0.678, that proportion of people passed the test. The claim is that 80% of people passed, so 0.80. And the standard deviation based on that claim would be 0.80. 80% pass, and that would mean that 20% don't pass, and divided by the sample size of 90. And if if I put that in the calculator right, I get negative 2.89. Okay. So that's the first part of step 4, is find this test statistic. That's the z-score that goes along with that data value based on that claim. And then I'm going to take that and I'm going to use that to find the p-value. Now remember, the p-value is the likelihood or the probability of getting that test statistic or that z-score based on the claim, or something more extreme. So the p-value is the probability that we get a z-score. Well, what do you think? Is it going to be greater than, less than, or not equal to? It's the same symbol we use in our alternative hypothesis. It's less than. Because to get something more extreme, or again, let me kind of draw up here. It's a z-score, so we're on a standard normal curve. I've got a z-score of negative 2.89. So the claim is somewhere up here, right? We are below the claim, and I want to know what's the probability of getting that claim that we, that percentage we discovered from our sample, 67.8%, or something lower than that, more extreme, right? So this would be less than. Well, to do this, I can just go consult my z-table or StatCrunch, but I'll just go dig this up on the z-table. Find the negative z-table. Find a score of negative 2.89. So negative 2.89. And there it is. It turned green. That's it. 0.0019. 0.0019. Okay. So this is equal to 0.0019. Meaning the probability of getting, if they claim that 80% of the people pass, then the likelihood of getting a group of people where only 67% of those people pass is only a 1.9% chance that's going to happen. Which makes us feel like, well, then I don't think that was just dumb luck and we happen to grab a group of bad drivers. I think the claim is wrong, because to get this number, it's incredibly unlikely. It's very low probability that we would get that or something worse than that. So the fact that we did get it makes us feel like the claim must be off, because we shouldn't have got that. It was too unlikely for it to happen. What I need to do now is I need to do the last step, step 5. How does that compare to my alpha, and what can I claim? Since our p-value is less than alpha equals 0.5%. Remember, 5% was what I would consider the lowest probability I'm going to deal with. And anything lower than that, I'm going to say that's too unlikely. The claim must have been off from the get-go. So since it's less than 0.05, we reject the original claim. We reject the null hypothesis. And what that means is that there is sufficient evidence to suggest that the true proportion is actually less than 80%. Percentage of people that pass is less than 80%. Okay, so again, this is an incredibly powerful topic. And in the beginning, I know you're just bombarded with this new process and new procedure, and it's a little confusing and maybe intimidating. I assure you that once you do 4 or 5 of these, you're going to be on autopilot because it's going to be the same thing over and over and over again, and you will just be able to do them backwards, upside down in your sleep. Guarantee it. Okay, you just need to keep doing it and do enough of them. And once they become a little more routine, maybe it's already kicked in now, but if not, by then you'll hopefully begin to see the power of these things. That what we've now done is we've unleashed the ability to let statistics basically make good decisions for us. And it allows us to take any sort of claim, any claim we want, and mathematically determine whether or not that claim is correct. It is an incredibly powerful thing we've just learned here. It just takes a little bit of time to get comfortable with it and to see that. All right. But again, you'll notice by the examples we do in class together, by the homework, that you're going to be doing this same process over and over and over, and it will become like autopilot. Okay. All right. Hope you hung in there. I would rewatch this example because this is the only example we did where we really did a true hypothesis test. All steps 1 through 5. Everything else in the notes up to this was kind of doing them in pieces. When you do a hypothesis test, this is it. Steps 1 through 5. Okay. Good luck and see you on the next one.